So good evening all. Uh, Welcome to the problem solving session for the seventh week for the course Geotechnical Engineering 1, which is handled by Professor D.N. Singh of Department of Civil Engineering, IIT Bombay, and I am Yogendra Narayanan. I am a PMRF research scholar who will be conducting this session every week on Saturdays 5 p.m. to 7 p.m. So now this session, to give a brief uh, prelude for this session, since it is getting recorded and will be available in the public forum, and many new attendees will be attending every week who may not have the idea of the purpose of these sessions. So these sessions are essentially to make the learners proficient in the concepts that has been taught in a particular week. So these sessions will be going on for the uh, 12 weeks of lecture, since it is a 12-week course, and one summary session will be there of for 1 hour, in which all the concepts that has been taught in this course will be revisited. And every week these sessions will be uh, conducted, wherein problems from the previous assignment questions, uh, and as well as some of the questions based on the concepts that has been taught on the lecture will be discussed by me, and the attendees will be solving the problems along with me, and mean by and in that and in that process they will be clearing the doubts whichever they have on how to approach the problem, or uh, right from understanding the question and how to which is the right approach for the problem. So with this, I would like to give a brief account of what topics and concepts has been covered in the week 7 of this course, Geotechnical Engineering 1. So essentially this week introduces the concept of flow through soils, that is flow of water through soils, uh, the concepts of head difference, Bernoulli's theorem, and quantifying the condition for the flow of water through the soils to occur, and the property which governs the flow through the soil, essentially permeability and hydraulic conductivity. Determination of these properties by various methods, by various laboratory scale methods and field scale methods. Laboratory scale methods involve constant head permeameter test and variable head permeameter test, and field scale studies involve pumping in, pumping out, and several borehole techniques, borehole measurement techniques. And subsequently, the determination of coefficient of permeability, which is also termed as hydraulic conductivity in case of layered deposits, and quicksand condition, the concept of a hydraulic gradient, and uh, quicksand condition, and what is the concept of critical hydraulic gradient to avoid the piping failure. And with this, and a small lead to the two-phase, two-dimensional flow through soils. So with this premise, we would like to get into the problems, and uh, at the beginning, just we will revisit the concepts and formulas through questions. At what conditions these assumptions are valid and these relationships are valid, and slowly we will be transitioning into the uh, problems from beginner, that is from easier problems to further mm, further increasing the difficulties of these numericals. So you are free to uh, interrupt me at any time, and you can ask me questions. And as well as if you are unable to attend these sessions, these will be uploaded in the public forum. Essentially, these links will be given uh, in the problem solving session options in the NPTEL interface, and in this you can access these slides as well as videos. And if you are watching the videos later, you can post these questions as comments also, and you can mail us in the ask a question tab in the NPTEL interface, which is provided to you. And these sessions will be uh, conducted every week on Saturdays 5 p.m. to 7 p.m. So I would recommend the learners and the participants who have registered in the course to make use of this opportunity to get accustomed with the questions, which might be useful in getting your concepts right, as well as in your as well as uh, it will be a big help in you attempting your final examinations, which will be probably held in April. So with this, let us move to the session. I hope the slides are visible. So essentially we will start with a basic revisiting of what has been taught. The first question obviously is, what is the unit of hydraulic conductivity? What is the unit of hydraulic conductivity? Option A, meter square per second. Option B, meter per second. Option C, kilogram meter per second. And option D, meters. So essentially we know that hydraulic conductivity is denoted as K, which takes the unit of meter per second. Now if we extend this question, so it should be here, I would like to point uh, a major conceptual uh, error which people tend to do. Hydraulic conductivity is always known as coefficient of is also known as coefficient of permeability. If we use the term bluntly as permeability, it is completely different from coefficient of permeability. The term permeability is denoted by capital K, which is the porous media property, which depends on the pore structure, grain size, etc. of the soil mass through which the flow is occurring. So hence it should be carefully noted that permeability is a separate term, and coefficient of permeability is also known as hydraulic conductivity. So this should be borne in mind whenever questions are being asked, and wherever you find this, you can, if there is a possible mistake, you can also rectify them, and you can also point out them. So in these sessions also there might be some of the questions where intentionally we have kept it as permeability. We might have kept as permeability. I would like to recommend. I would like the learners to point out these mistakes and uh, point out these uh, intentional mistakes, and rectify it. So we know that here the unit is meter per second. And now what is the unit of permeability, which is a porous media characteristics? So its unit will be meter square. It will be meter square. It should be borne in mind whenever you are solving the problem. Meter square per second. The other options which we look, square per second, we'll be studying the quantity which is used to denote by this term further in this course. Meter is obviously length, kilogram meter per second is obviously the force, and second square obviously is the force. This essentially is the momentum. Mass into velocity is the momentum term, and this part is, even though it denotes velocity, hydraulic conductivity is also the length covered in a unit time, hence by water in the porous media. Hence, hydraulic conductivity is also denoted by meter per second. I hope I am clear now. Let us move to the next question. What all properties of fluid will on the depend upon the coefficient of permeability? So what all properties of fluid will depend upon the coefficient of permeability? Will depend upon the coefficient of permeability. So this can be rephrased. Like to just it can be replaced will affect. So option A density, option B viscosity, option C temperature, option D all zero. Now let us analyze the options one by one. So first option is density. So density of the fluid, we know we have. So who have joined now, you can just uh, uh, start starts noting down from the second question. So I'll repeat it again. Am I audible?
Yes, sir, is audible.
Are you able to see the slides?
Yes, sir.
Okay, you can start from the second question. So what what all properties of fluid will affect the coefficient of permeability? What all properties of fluid will affect the coefficient of permeability? Option A density, option B viscosity, option C temperature, and option D all of the above.
All of the above, sir.
Okay. Can you uh, explain how these parameters affect the permeability of this affect the coefficient of permeability?
Uh, Permeability formula, which is equals to permeability formula depends upon the porous media and fluid.
Yes. So you are right. So always coefficient of permeability will depend upon the is a function of fluid properties and porous media characteristics. So fluid properties include density. If a fluid of two different densities are flowing, for example, water and uh, gas uh, is flowing, obviously there will be a difference in uh, flow of uh, flow between these two fluids through the soil mass. And viscosity, we know that uh, if the fluid is highly viscous, obviously its flow through the porous media will be restricted due to the uh, resisting nature of the viscosity. And temperature, when it comes to temperature indirectly affects these two properties. And if the temperature of the fluid is higher, the viscosity of the fluid will be lesser, as well as the density of the fluid will be lesser, which in turn affects the coefficient of permeability. So these three parameters obviously will affect k, small k, and hence the option will be all of the above. So moving to the next question. So what is the pressure along the phreatic line? Lesser than atmospheric pressure, higher than atmospheric pressure, equal to atmospheric pressure. It can be both lesser or higher depending upon various situations. What is the pressure along the phreatic line? Can you answer this question?
I don't know, sir.
Okay. Do you know what is phreatic line? Do you know what is phreatic line?
I know, sir, but I don't know how to explain. So
Yes. Try to explain. There is no issue. Okay, let me explain this. So phreatic line, yes,
the phyretic line is separated saturated water and unsaturated water.
yes. So a phreatic line always separates the
Soils, sorry.
uh, so it is the boundary between the saturated zone and vadose zone or unsaturated zone. So it is in real life conditions, the groundwater table, the presence of groundwater table itself is the phreatic line. So how to the to be technically the definition of phreatic line is the uh, level of water which is always at atmospheric pressure, right? So wherever if you consider you consider a soil deposit here and you have a water table here. So if you keep a piezometer, will it rise or not?
ఏంటి రైజ్ అవుతాయి కదా క్యాపిలారిటీ రైజ్.
No. Assume that there is no capillarity. You keep if you keep a capillary tube, then only it will rise. If you keep a piezometer,
నో సార్.
so why it does not rise? And uh, to be let me give another situation. You take a point here and you keep a piezometer here, what will happen? To what point it will rise?
Water up to water level.
To water level. So that is termed as pressure head,
Pressure
right?
head.
Right. Now that is it will rise up to the point where atmospheric pressure is acting. So if it rises, it can be also phreatic line can also be defined as up to the points up to where water level rises when you keep the piezometer, right? So it marks the atmospheric pressure. So essentially, the definition of phreatic line is the level of water which is always under atmospheric pressure conditions. So the correct option will be C. So now you please keep in mind this terminology, phreatic line, and its significance. It will be very useful in the next week lectures where you'll be studying flow through the earthen dams. So these terms are fairly important, uh, and also in attempting the effective stresses problems, you might need to know sometime the phreat instead of groundwater table they might give us phreatic line and etc. So this will be under atmospheric condition. So moving, I hope it is clear now. Or you have any doubts?
Clear, sir.
Okay, let us move to the next question. So what are the field tests carried out to determine the hydraulic conductivity? What are the field tests carried out to determine the hydraulic conductivity? This is a fairly simple, straightforward question.
Pump in, pump out.
Yes, pumping in and pumping out tests are there. And here, Packer test is also a field test. Pumping in and pumping out test will be uh, to it is like how you carry out borewell installation in our homes. It is similar to pumping in and pumping out test is what we do is borehole uh, drilling. And Packer's test is a way of measuring hydraulic conductivity within that borehole itself, at that site itself. If you have a ground level and you have an aquifer or water table here and you want to extract it, so you drill a borehole and here itself you measure the permeability by keeping some packers. So this is known as Packer's test, and Packer's test also can be used to study the coefficient of permeability through rocks. So all the three are field tests, and hence the option is all the above. Hope it's clear now.
Okay, sir.
And moving to the next question, what is the mathematical form of Darcy's law for a laminar flow for the given, which are the given uh, terminologies? How is Darcy's law defined?
V is directly proportional to I.
Yes,
So V is equals to Ki.
yes. So can you list some of the assumptions in Darcy's law? Can you list some of the assumptions of Darcy's law?
Flow is laminar.
Yes, that is one. Second,
Standard temperature.
uh, laminar flow. Not standard temperature. There are some
Okay.
corrections for temperatures also, but at this level it is right at normal temperature ranges.
Okay.
And third one, this relationship is valid for fluid which is incompressible, like water. Water is considered to be incompressible. And another main assumption is soil should be saturated. Is SR equal to 1. So this relationship, this simple Darcy's law is valid for saturated soils for a flow of incompressible fluid with a normal pressure temperature condition when the flow is laminar. So what is the condition for laminar flow?
Reynolds number less than 1.
So what is obviously to lead to the next question? What is the mathematical relationship for Reynolds number?
Rho Vd by mu.
Mu. So rho is the density, v is
V
the
is the
velocity,
velocity.
and
D
d
is
is
the
the
direction.
characteristic length. Here it is grain size. By mu is viscosity.
Viscosity.
So what should be the limiting value for Re for the flow to be laminar through the soils?
I think less than 1. Flow is laminar.
Re should be less than 1. This is valid for soils only. In case of pipe flow, Re will be less than 2000. That is not necessary here. So uh, you can, for soils, for the condition for the laminar flow to occur is Re is less than 1. So let us move to the next question. Hope it is clear now. If, or
Yes, sir.
you have any doubts?
No, sir.
Okay. Now select the correct statements. Constant head test is preferred for granular material. Falling head test is preferred for fine grained soils. And constant head test is preferred for fine grained soils and falling head test for granular soils. Which of the following statements are correct?
First two.
Yes. First two are correct. Can you explain why constant head test is preferred for granular material and falling head test is preferred for fine grained material?
Constant head test. The head difference is sorry. Fluid water is how I don't know how to explain, sir.
Okay. So which type of soil has relatively higher hydraulic conductivity? Granular soils will have higher hydraulic conductivity, or fine grained soils will have hydraulic conductivity higher.
Granular soils, soils.
right? So simple permeability test is you prepare a soil column and you maintain a head above the soil column, right? Now this is fairly, if it is coarse grain material or granular material, its hydraulic conductivity will be in the range of 10 power minus 3, 10 power minus 4 uh, meter per second. In case of fine grained soils, it will be 10 power minus 4, 10 power minus 7, 10 power minus 9 approximately meter per second. Right? Now you consider you are conducting a falling head test for granular soils. So you will prepare a sand column and you will be maintaining a head and you will start your timer to measure the discharge. What will happen to the discharge here? Any idea?
Sir, once asked me.
So see, let me put like this. So you are preparing two soil samples. One is of coarse grained, that is granular. Another is of fine grained. And in both tests, both samples you are conducting, let us say falling head tests. I hope you remember what is falling head test.
Yes, sir.
This is the water. Now you are starting the experiments. So what will happen to the fall in head for coarse grained compared with fine grained?
In coarse grain soils, falling at test and water is suddenly dropped.
Suddenly dropped. So you cannot measure the time interval and the head drop at a particular for a with the uh, you cannot measure the fall in head as well as the time for that quick drop in head, right?
Yes, sir.
So to avoid that, what people will be doing is they will be constantly pouring, maintaining this head as constant. Now, if you take a same case, now you want to conduct a constant head test for fine grained soil. So you will keep the head for how much time? You will be keep this experiments will take almost 2 3 days to occur. So you cannot always monitor and maintain the head, which will drop maybe one centimeter, 1 millimeter per 2 hours, 3 hours. You cannot also keep on filling the uh,
Water.
maintaining the head like that. So hence people came up with the measurement of falling head method for fine grained soil and constant head method for coarse grained soil. So that is the simple reason, uh, which is a common sense, which is uh, due to which we are following constant head test for granular material and falling head test for fine grained materials. I hope now I am clear now. Are you able to
Yes,
understand?
sir. Yes,
Right.
sir. Understood.
So this problem we will be visiting a little later. So you can solve this problem. A glass cylinder with a cross-sectional area of 50
Sir, once
centimeters. Yes,
Sida next before phase, sir.
yes. Now this problem we will be solving a little later,
Okay, okay, sir.
right? So you can you can solve this problem now. A glass cylinder with cross section 50 centimeter square and length 40 centimeter is filled with saturated sand having porosity 0.4. Water maintained at a constant head of 20 centimeter is allowed to flow through soil mass for 30 minutes and is collected in the measuring jar. Assume the hydraulic conductivity of the soil as 2 into 10 power minus 3 centimeter per second. What is the seepage velocity? Can you solve this?
Sir, explain, sir.
So now what are all the parameters given? Cross-sectional area is given, which is 50 centimeters square, and length of the soil sample is given 40 centimeters, and porosity is given 0.4. Right. Now we know the maintained at constant head of 20 centimeter is the head the head that is responsible for flow is how much? 20 centimeter, right? And given is hydraulic conductivity, they have given 2 into 10 power minus 3 centimeter per second. Now what is the formula for, now we know that V equal to K I, right? Now, and we know that seepage velocity Vs is how much? So what is the relationship for Vs? So what is the relationship for seepage velocity?
V by N.
V by N,
N.
porosity, right? Now we need to calculate this, for which we have porosity, we have already have, and we need this one. Now for calculating this, we know that V is equal to Ki. This is Darcy's law. Now, right now, I, how will you calculate? We know H, V is equal to,
Okay.
we know this part, K, and I is 20 by 40. I is defined by H by L, head loss by L. The total head loss is 20, and this is 20 by 40. How much it comes to be? 10 power minus 3 meter per centimeter per second. Right?
Option B.
Check carefully. So you have V. What is Vs? 10 power minus 3 by 0.4. How much it comes?
2.5 into 10 to the power of minus 3.
Minus 3. Now you calculate the discharge. Can you calculate the discharge?
Yes, sir. Wait a minute. Fifty into 10 to the power of minus 3 centimeter cube per second.
Yes. So that will be discharge. And you calculate how much volume? So Q will be 50 into 10 power minus 3 centimeter cube per second. So you calculate if discharge is this, you have time for 30 minutes. How much water will have been collected? Are you calculating?
Yes, sir.
How much you
Um,
are getting?
90 into 10 to the power of 90,000 in. Sir,
Yes.
90 into centimeter cube per second.
Not a centimeter cube per second. Now you are multiplying with time, na? It will be centimeter cube only. Q will be 50. That is total volume will be
Okay, 90 centimeter cube of
90
second.
centimeter cube.
Cancel. Okay, okay.
Right. Now let us move to the next question. A coarse grained soil has a Voigt's ratio of 0.75 and a specific gravity 2.75. The critical gradient at which quicksand condition occurs is. Can you answer this question?
I don't know, sir, formula.
So what is the critical hydraulic gradient formula? IC is equal to G minus 1 by 1 plus E. Now you can calculate 2.75 minus 1 by
1.
plus 0.75. So it will be 1. Right? So
Yes, sir.
this is the formula for IC. Whenever, so piping means soil will lose its integrity. And now always the hydraulic gradient should be lesser than IC for the piping failure not to occur. So here Then now uh, you calculate this question. What is the effective permeability of an anisotropic soil having permeability Kx equal to this much and Kv equal to this much? So here let me give this uh, just effective permeability. You have K horizontal and K vertical. When you have this, and the effective permeability will be root over Kx into Ky. You just take the square root and you use this formula to get this. Please solve and let me know the answer.
Six.
6 into 10 power minus 4. So now that the previous question, now you can calculate in this. It is similar to the previous question, but little bit extended, and the concepts start earlier were also incorporated. So you can uh, solve this question. And during examinations, you will be expecting these kinds of questions only. So it will be interlinking various concepts for which you need to remember all the topics that has been covered, because every topic is interrelated. So obviously the questions will be interrelated. So you can solve this question. What is the critical hydraulic gradient for a soil having maximum and minimum voids ratio as 0.6 and 0.4 respectively and relative density of 70%? Calculate the critical hydraulic gradient. Assume GS equal to 2.67. Can you do it?
Yes, sir.
So we know that relative density is equal to E max minus
I
E,
think 1 point.
E max minus E min, which will be zero point 0.7. Just check your steps are right or wrong. 0.6 minus E by 0.2, which will be here 0.14. E will be 0.36. Sorry, 0.46. Right?
Sir.
And IC will be J minus 1 by 1 plus E, which will be 2.67 minus 1 by 1 plus 0.46. 1.67 by 1.46. How much you are getting?
Sir, option is not there, sir. 1.14.
Okay. 1.67 divided by 1.46. 1.14. So this option you can change it a little. Yes, 1.4. So this is the right option, right? Now moving to the next question. Uh, Now, during a falling head permeability test, the head passing flow was initially 90 centimeter, which dropped by 6 centimeter within 15 minutes. How much time will it take for the head to fall to 45 centimeters? Now you calculate this part only. During a falling head permeability test, the head causing flow was initially 90 centimeters, which dropped by 6 centimeter within 15 minutes. How much time will it take for the head to fall to 45 minutes? Can you solve this? This part can you solve? We'll be solving one part at a time. Can you solve this question?
I will try, sir.
Yes. So you can try. Uh, I will be back in just a minute.
Okay, sir.
Log of this equal log of this.
అంతేనా?
ఆ మిగిలిన క్యాన్సిల్ సేమ్ పెరిమిడిటీ ఉంటుంది కదా.
మ్మ్.
Have you solved the question?
No, sir.
Okay. So let us solve together. So see when uh, let me just explain the question. This you have this is the soil sample. Right. Now let its thickness be L. Right. And this is the area of cross section, which is denoted by capital A. Right.
Yes, sir.
Now you have this part, which is denoted by small a. Right. Now, what is the formula for falling at perimeter? So
Two
KL
point.
is equal to
Okay.
2.303 into small a into L by capital A into T log to the base 10 H1 by H2. Now you have two conditions here. First, it is falling from 90 centimeters to by 6 centimeters, which is 84. Right. Now second part is it has to fall from 84 centimeters to 45 centimeters. Right. So in this both the condition, which parameter remains constant?
AL by A
AL by A and
and permeability
permeability is constant.
and
So
2.303.
that will and now this part will be, you can equate, right? So 2.303 into A into L divided by A into time is 15 minutes into log of 90 by 84 is equal to 2.303 into AL by A into time required log 10. Now it will fall from 84 to 45.
Sir, 90 to 45 is.
No, see, for first 15 minutes, it fell from 90 to 84. Now it will take from 84, it has to fall to 45. Now uh, you can first you calculate this part. Uh, this is what is being asked now. So you can cancel this, you can cancel this, you can cancel this. This part will go. It will be. Can you calculate and say?
Sir, I solve 90 to 40 falling head is 90 to 45. I solved, sir.
Okay, can you solve this now?
Okay, sir. 135 minutes.
35 minutes. Okay. Now you
Remind
solved
me.
for 90
Mm,
to 45. Now how much you are getting?
150.
So both you can do by both the methods if asked. 135, it is already 15 plus 15, it will be 150, right?
Okay, sir.
So
Sir, I have a small doubt. In a
yes,
question, how to find, sir, ante because of 90 to 45 or 84 to 45, how to find?
okay. In that case, uh, they will give the question will be given how much time further it will take to fall to 45 centimeters. Like that, if it is coming, you have to calculate this part only, 135, that part only. Here they have mentioned how much time it will take for the head to fall to 45 means it is obviously from 90 and 45. If you are not clear, you can just write in the sentence, it will take 135 minutes to fall from 84 to 45 and it will take 150 minutes to fall from 90 to 45. You can write that clearly.
Okay, sir.
Okay. Now you consider this capital A as 100 centimeter square and thickness of the sample same as earlier question ones we considered, right? 40 centimeters. And this small a you consider as 10 centimeter square. Now you calculate the permeability. How much you are getting?
Wait a minute, sir.
Mm.
Call.
Okay, okay.
Uh, 0.018 centimeter per minute.
Okay. 0.018
18
centimeter per minute.
minute.
This is hydraulic conductivity, small k, right?
Yes, sir.
Now you have the viscosity of water at 25 degrees centigrade is this much. Now calculate the absolute permeability, which is intrinsic permeability denoted as capital K. Do you remember the relationship?
Yes, sir.
Hmm. Now you can calculate. How much are you getting?
Wait, sir. Wait.
What is the density of water?
1 gram per cc.
Yes. So it is straightforward. So K will be, sorry, K will be K into gamma W by mu. How much are you getting?
Sir, 2.733 into 10 to the power of minus 9.
Meter square, right? So it will be, its unit is meter square.
Centimeter square, sir, I think.
Centimeter square. Okay, fine. So let us move to the next question. So a horizontal stratified soil deposit consists of three uniform layers. The following data is available. For the top layer, K is this much, thickness 7 meters. For middle layer, K is given and the thickness 3 meters. And for the bottom layer, it is 6 into 10 power minus 4 centimeter per second and thickness is 10 meter. Find the ratio of average permeability of the deposit in horizontal to vertical direction of flow. Can you do this?
Explain, sir.
See, now always try to translate the given questions to figure. So you have three deposits. Right, it is not to the scale. So that's it. To be 7, to be 3, it will be almost 10. So it is 7 meters, it is 3 meters, it is 10 meters. Now its permeability is 8 into the power minus 4 centimeter per second, and its value is K equal to 52 into 10 power minus 4 centimeter per second. Its value is, this is, let it be K1, this is K2, this is K3, 6 into 10 power minus 4 centimeter per second. Now first condition is water is flowing like this. This corresponds to vertical flow. And second condition is water is flowing like this. It will be Q, some Q value. Right, this is horizontal flow. So vertical is KV, horizontal is KH. Now what they're asking is kH is to kV is how much? Can you do this? Do you, did you understand the question now?
Yes, sir. Understood.
Can you do this now?
Yes, sir.
Okay.
1.7666.
Okay. So how did you calculate? KH is
KH
K1 H1 plus K2
K2 H2
H2
plus
plus K3
K3 H3
H3 by
H1
sigma
plus
H
H2 sigma H
and KV is
sigma H
sigma
by
H by H1 by
H1
K1
K1
plus
plus H2 by
H2 by
K2.
K2 plus H3 by K3. You can note that KH will be always greater than KV. So if you substitute these values, you will get whatever value you got, approximately 1.77, which can be approximated to 1.8, right?
Sir.
Okay. Now we can go to this question. For the soil deposit depicted in figure, assume an average hydraulic gradient of 0.5. Determine the head drop between the top and bottom of layer 2 for the flow in vertical direction. What are you understanding from this question?
Find out H2 in layer 2.
Yes, right. And do you know how to do it?
I will trace.
Yes.
Sir, explain, sir.
Okay. So now we have these three layers, right? Now they have mentioned that assume an average hydraulic conductivity of 0.5 in both the direction. So average hydraulic conductivity is, if you calculate the effective hydraulic conductivity, you will have a single layer with K effective and I effective, right? Are you getting now? Hello?
Sir, I effective means?
I effective is if uh, hydraulic gradient between this point and this point. So
Okay.
that they are asking you to assume it as 0.5.
Okay, okay, sir.
Now you have K1, K2, K3. You calculate K effective now for vertical flow.
K effective is equals to 3.06
Okay. Into
into
10 to
10
the
to the power
minus
of
4.
minus
Minus
4.
4. You are getting, that is right. 3.06 into 10 to the power minus 4. Now in vertical flow, which will be constant? I will be constant or Q will be constant? See, here flow is taking place downwards, right? Like this. Are you able to understand?
Yes, sir.
Now
Discharge is constant.
discharge is constant, and we know that you consider a particular area. So discharge is constant means velocity is constant. So V, that is Q1 equal to Q2 equal to Q3 equal to Q, right?
Sir.
Now which layer we want? We want layer 2. So we will take this relationship. Q2 is equal to Q. Now Q is will be K effective into I effective into A. Q2 will be K2 into I2 into A. Now A will get cancelled. K2 you know, K effective you know, I effective you know, you can get I2. Right? Are you able to understand?
Yes, sir.
Now you calculate I2. It will be 3.06 by 3 into 0.5. How much you will be getting? I2 will be
0.51.
0.51.
5.
Now you need head drop. So I2 is head drop by thickness of the sample. Now you need H2. L2 you know as 5. I2 you know as 0.51. 0.51 into 5. How much you are getting?
2.55 meters.
2.55 meters. So this is the head drop between layer 2. Now you calculate for layer 1 and layer 3.
Okay, sir. First one is H1 is equals to 0.918.
Okay. Third one.
1.53.
Okay. Yes. So now you can understand this part, right? Now, hello.
Sir,
Okay. Now you take horizontal flow and you take I as 0.5. Now you calculate discharge for which.
Then
Now you know that Q total Q1 plus Q2 plus Q3, which is can you calculate this?
yes, sir.
Okay.
Sir, where hydraulic gradient is constant?
Yes, obviously in horizontal flow, hydraulic gradient has to be constant.
Okay.
Discharge will be different.
Sir, first one is 1.5, H1 is equals to.
No, no, just you calculate discharge through each one. Here H will be constant, right? There will
Yes,
not be different H. You calculate discharge through this, and this. It is fairly simple. It will be K1 into L1 or capital H1 into I. Because Y means, listen here for a moment. Now you are assuming that flow is taking place through this portion. Now always this is cross-sectional area. We have the thickness. Always if thickness is not given, we'll be assuming 1 meter in the other side. So it will be H1 into 1. So we know that Q is equal to KIA. Q1 is K1, I you know, and A is H1 into 1. So it will be K1, which is 5 into 10 power minus 4. I will be 0.5 into H1 is 3 into 1. Now you can calculate discharge here. Are you able to understand now?
yes, sir, understood.
Now you calculate for all the three.
Total discharge is equals to 7.
Okay. Separate discharges.
First layer 7.5.
Total you are saying 7. How first layer will be 7.5.
Sir, I forgot to convert meters into centimeters.
Are you getting?
Sir, firstly 7.5 into centimeter cube per second, sir.
Okay. Second?
Second is also 7.5 centimeter cube per second.
Okay.
Third one is 2 centimeter cube per second.
Okay. Hmm. Right. Okay. Now, um, now let us move to the next question. A masonry dam has its foundation on the pervious sand deposit. Determine the maximum upward hydraulic gradient if a factor of safety 4 is required against boiling. Consider the porosity of sand as 45% and its specific gravity as 2.65. How will you solve this?
First we calculate critical hydraulic gradient.
Yes. How much you are getting? You have porosity
For 45% and
45.
0.45.
I will convert to E.
E is equals to porosity
1 minus equal to V by 1 plus E 0.45 plus 0.45 E is equal to E 0.45 by 0.55 is equal to E. How much E you are getting? Hello? How much E you are getting?
E is equals to 0.818.
0.82. Now you calculate IC. C is G minus 1 by 1 plus E. 2.65.
0.906.
Okay. 0.906.
6.
So this whatever I this is critical hydraulic gradient at which boiling occurs. So you know factor of safety is 4. You have to keep now what is meant by factor of safety? Factor of safety is I by IC by I. Right. Now how much I you will be getting? I should be IC by factor of safety. You have to divide 0.906 by 4. You will get approximately 0.22 something. How much you are getting?
0.2266.
0.226. Okay, let us move to the next problem. So a pumping test was made in pervious gravels and sand extending up to a depth of 16 meters where a bed of clay was encountered. The normal groundwater was at the ground surface. Observations well were located at distances 3.5 meters and 8.25 meters from the pumping well. At a discharge of 18 meter cube per minute, a steady discharge state was attained in about 24 hours. The drawdown at a distance of 3.5 was 2 meters and 8.25 meter is 0.6 meter. Compute the hydraulic conductivity. Now you make the figure. This is the ground surface, right? Now you are encountering a clay layer here. So it is 16 meters. Initially, the level is at ground level. Water level is at ground. Now you are taking out the water and you are drilling two observatory wells, one at 3.5 meters, one at 8.25 meters. Now what will happen? Initially this was here. Due to pumping out, it will go here, further, go here, there, go here. A similar way it will go like this. Right. Now this drawdown at 3 point, this is 3.5 meters and this one is 8.25 meters. This is drawdown, which is H1. Not this is H1. This is sorry H1, H2. We know this part. This is 2 meters and this is 0.6 meters. Now what is the formula for hydraulic conductivity? K is equal to 2.303 Q by pi into H2 square minus H1 square log 10 R2 by R1. Are you able to understand?
Yes, sir.
Now how will you calculate H2? It will be 16 minus 0.6. H1 will be 16 minus 2. Now you substitute everything and let me know the answer. You can do this from here, na? Can you do this now?
Sir,
R2 is 8.25.
okay, sir. 0.12.
What is the unit? Unit.
Meter per minutes.
Okay. So V 0.2 meter per minute. Right. Now let us solve this question. Right. A sand layer of the cross-section area as shown in the figure below has been determined to exist for a 800-meter length of the levee. So this is the levee, right? This is impervious, right? Hello, are you able to hear?
Yes, sir.
This is also impervious. I hope this is clear.
Okay, sir.
Now the hydraulic conductivity of the sand layer is 2.8 meters per day. So this is the sand layer. Its hydraulic conductivity is K is equal to 2.8 meters per day. Determine the quantity of water which flows into the ditch. If the sand has a first you can calculate this. Now, what are all the informations you have? Can you say what are all the informations you have? Hello?
Sir.
What are all the information you have in this question?
Flow L and the space G.
L you have 180 meters. Let us do the first part only. Now, then we will go to the second part. L is 1.180 meters and K you have, right? You need Q. Q is equal to KIA. For A, you have the thickness 1.6 meters, right? Hello?
Yes, sir.
You have 1.6 meters and it is extending this side into the plane up to 800 meters. So the area will be 1.6 into 800, right? Are you able to
Yes, sir.
understand?
Yes, sir. Understood.
I now you know K is equal to it's Q equal to K into delta H by L into A. You have A, you have L, you know K. What is the delta H?
15.
Yes, it is 15. So now you can substitute everything here. How much you are getting?
298.298
298 unit.
meter per day.
Meter or meter cube?
Wait. Meter cube, sir.
Meter cube per day.
Day.
Right. Now the property of sand is given. You calculate the seepage velocity now. ES is
E cut.
V by N. N you know as E by 1 plus E. How will you calculate E? You know the dry density. Gamma D is equal to G gamma W by 1 plus E. So from this you calculate E. Did you understand?
Yes, sir.
You can get E now.
Uh, where void ratio is equals to 0.62
Okay.
and porosity is equals to 0.38.
Okay.
0.
How much you are getting seepage velocity? Just divide the area with just divide the discharge with area and you will get the V value and you get the porosity. You already know the porosity value.
I think 0.614
Unit.
meter meter per day.
Okay. Yeah. So now you understood, na?
Yes, sir.
Yeah. So there are two more questions. If possible, you can solve this. But now the time is over. If possible, we will continue in the next week these two questions. Right. These slides will be uploaded in the NPTEL website in your account in your from your login. You will be able to access these slides. And with this, we can conclude this session today. If you have any
Okay.
doubts, you can always mail in the. You can always write in the Ask a Question tab in the NPTEL account you have, and most probably we'll discuss these two questions in the next week also. Right?
Okay, sir.
Okay. Thank you.
Okay, sir. Thank you, sir.